Hello, welcome to AP Physics, and we are going to be doing an example problem. The example problem I'm going to be doing is an example that is from your book, and this is on conservation of momentum. And it's a little bit of a tricky problem, and so I wanted to help you guys out with it. So this is the problem. A bullet, a 10-gram bullet, is fired into a 1,200-gram wood block hanging from a string. The bullet embeds itself into the block, and then the block swings out at an angle of 40 degrees. What is the speed of the bullet? All right, so I'm going to draw a setup. This is always kind of the first thing that you should do of this situation. So we're going to have a bullet that is going to travel. I'm going to call that mass 1. Okay, a bullet is traveling at a certain speed of v1. So it's traveling that speed. We have a block that is hanging from the ceiling. Okay. That block is not moving. It has a length of the string to the center of mass of the bullet. That is the length L. The bullet embeds itself into the block, causing it to swing. So I'm going to show just the moment when it embeds itself. So it's in here. And then the combo is going to start to be moving. I'm going to call this V2. And then that is going to swing up. And we are going to have a third situation where the block and the bullet swing up at an angle of 40 degrees. So we need to figure out what the velocity of the bullet is. What we know is the angle of the string is 40 degrees. How do we do that? Okay. This is a conservation of momentum question, so I'm going to kind of just start from the beginning and see what it is. So at the beginning, we have our momentum before, which is just the bullet, right? So it's mass 1 times v1. Right now, I'm just going to be using letters. If I started to plug in numbers, it's going to be way too confusing. So we're just going to represent the numbers, okay? After it hits, just that moment it hits, the two are going to be moving at a speed, but they're going to start to slow down because it's going to go up. So I'm going to look at the situation, the momentum after. Just after they hit is going to be the combined mass, M1 and M2, times the speed of both of them together, V2. This is an inelastic collision, and that's all we have to worry about. Okay, but then it goes up to a height. Well, how do we use that height to figure out that? I want you to think about what concept is going to help us to figure out how its angle is going to be represented in figuring these things out. Okay, we do want to use conservation of energy in this case. That's going to be the best answer. And there is going to be the block and the bullet are going to go up a height. How high they go depends on the angle of the string, and we know what that angle of the string is. The string itself is a distance L. Okay. The distance from the height plus this extra distance right here, and this is going to be a common kind of question that you are going to do, is going to be a total of L. Now, how do we get that? This height plus the distance right here from the bottom to the top is the distance of L, because this is a distance of L over here. So H plus whatever this little distance is right there is going to be L. Well, what is that little distance? Okay. That little distance, I'm going to draw a line right here, is represented by a right triangle. Our height is down here. And then we have that little extra distance. By using our understanding of trigonometry, we can say that this is going to be L, and it's the times cosine of the angle. You see that? So H plus L cosine of the angle is going to be equal to L. That little extra bit was L cosine of the table plus a height. What we need is height because we're going to use potential energy. So height is L minus L cosine of theta, which is L times 1 minus cosine of theta. Like that. Okay, I'm just using letters right now to do that. So what does that give us? Well, that's our MGH, our potential energy. I should use U equals MGH. And we have the M right there. This we have the H right there. The M is both M1 and M2 combined. All right, so at this point, there are two steps. We have momentum before and momentum after. This is conservation of momentum. Then we have the energy before and the energy after. That is going to be also conserved. Energy in the swing, momentum in the transfer of these things. So I'm going to work out these two things with energy. And then we're going to work out these two things with momentum. All right? So the energy is the speed at the bottom. Our kinetic energy is going to equal the potential energy at the top. So our energy at the bottom is 1/2 of M, which is both M1 and M2 combined, times the speed of that unit squared before it starts to climb, equals M times G. I'm gonna, using a Sharpie isn't the greatest. M1 plus M2 times G times H. And the nice thing about this with energy is the M's cancel. And we get our V2 squared equals 2 times GH. Do you see that? V2 squared equals 2 times GH, or V equals the square root of 2GH. And what's H? H is our L times 1 minus cosine of theta. Okay. Now we know what our V2 is based on energy conservations. Now we're going to go to momentum and do that. And it'll get too confusing on this, so we're going to go to another sheet. Okay, the conservation of momentum is going to say that momentum before is going to equal the momentum after, which is the M1 times V1 is the momentum before from our picture over here, equals the M1 plus M2 times V2. Well, we know what V2 is now. It's the square root of 2GH. 2GH, and H is L times 1 minus cosine of theta. Okay, so we do know those things. And what we're trying to figure out is what the momentum is before. So V1 equals M1 plus M2 over M1 times our V2, which is the square root of 2GH. And now I'm going to put in what that equals. M1 plus M2 over M1 times the square root of 2G times 1 times L times 1 minus cosine of theta. Whoop. A little bit confusing there. And then we plug in some numbers here. Okay, we need to use our mass 1 is 0.01 kilograms. We need to use kilograms. Mass 2 is 1.2 kilograms. Boom. Our L is 0.1 or 1.5 meters. That's our L, and our theta is 40 degrees. So V1 equals 1.21 divided by, it was a 10 gram going into, 1.21 divided by 0.01 times the square root of 2 times G, and we'll plug in 9.8 for G when we get to it, times L, which is 1.5 times 1 minus the cosine of theta. Okay? So now we're going to use our calculator to calculate some of this stuff. At this point we can do that. I'm going to do what's inside of the square root first. 2 times 9.8 times 1.5 times, in parentheses, 1 minus the cosine. Make sure you're in degree mode of 40 degrees. And we get 6.88 significant digits. So 1.21 over 0.01 times 6.88, which I'm going to multiply that by 1.21 divided by 0.01 is 832 meters per second. That is our speed. And that is somewhat of a complicated problem right there, where we had to use energy and momentum to find the solution to the problem. Some of you may have noticed a mistake that I did in my original thing here. And so I'm going to finish this. I forgot to square root the 6.88. And so I'm going to recalculate this. The square root of 6.88 times 1.21. Oh, the square root of 6.88 times 1.21 divided by 0.01 is 317. So the velocity should have been 317 meters per second instead of that.